Thank you very much. I appreciate the invitation to give this presentation to you all today and give you an overview of the work that myself and many of my colleagues have been doing for the past over 4 years now. I'm going to give you a very short overview using PowerPoint, and then going to dive into a live demo of the system, which any of you can access. It's freely accessible to anyone in the world. So the dashboard is available at this particular URL. If you just search for CompTox dashboard, you will find it. It should show up very quickly in your Google searches. Freely accessible to everybody. It's an integration hub for many data sets, interagency collaborations in terms of how we're connecting websites together. It pulls together the resources delivered by many other agencies, as well as international organizations that we are plugging things in. We've taken on the hard job of assembling the data into a form that can be delivered through one homogeneous interface. It integrates multiple databases underneath, but then it links to these other resources. So that's why we think of it as an integration hub. We have 875,000 substances at the moment. The majority of these have structures, but they are substances, so you will find things such as tallow oil, rose oil, things like this. We can't draw you a chemical structure. Also very complex chemicals such as C12 to C16, linear, alkyl benzene sulfonates. We can't draw you a specific structure. These are complex substances, but we can still pull together data. While many people use it simply to enter and search based on chemical, using names or CAS numbers as examples, we do also allow searches by product use and gene, because we've integrated a lot of our bioactivity data. So if you want to know what's in toothpaste, search on the product use toothpaste, and it will show you all the chemicals we've been able to pull together around particular product types. I will show you that as we go forward. We've been pulling together experimental and predicted data from various sources. The experimental data we try to curate to the highest level possible. We have both built our own predictive models. I will be showing you today two of those tests. They're called TEST, Toxicity Estimation Software Tool, and OPERA, which is our suite of prediction models for PhysChem and environmental fate and transport. Also fully available as open sources, so you can download the models on your side and reuse them. We've done the same for bioconcentration factor, bioaccumulation factor, etc. So not just PhysChem, but fate and transport. The ToxCast, Tox21, interagency work that's been going on to measure a few thousand chemicals in a couple of thousand bioassays. All of those data are now available through the dashboard. We've integrated directly to Pubmed so that you can use our database of chemicals as the basis of searches into Pubmed. I'll show you that module. This link to other agency websites, we've built a link farm that at the moment hosts over 70 different links that allows you to search for different types of data that we can't host. We can't do everything, and there are so many other websites working hard to deliver data to the community. We want to take advantage of those efforts. We don't just give you one chemical at a time. If you had 5,000 CAS numbers, 5,000 chemical names, and you wanted to source data from our site, I believe we have a fairly unique position at the moment for a website serving up chemistry and toxicity data. We do this batch searching capability, so we'll walk through that. We've been building lists of interest, so depending on who you are, how you would want to use the website, this particular group may be very interested in pesticides. Other groups may be interested in looking for chemicals that are being analyzed by mass spectrometry in water. Other people may be interested in PFAS chemicals, the perfluoro and polyfluoroalkylated substances. All of the data is downloadable for reuse and repurposing. Everything we do is for you to take advantage of, so that you can take the data away from the website and integrate into your own systems. So it's a single application integrating this search capability. And you can see here in the 3 tabs, chemicals, product use categories, and assay gene. We are delivering various types of data, including toxicity, bioactivity. We do all these automated searches in the background to speed things up for you. So if you're looking for similar compounds, we will deliver that directly through a tab. We have an integrated read-across system built in called Generalized Read-Across, developed by my colleagues Imran Shah and Grace Patlovitz. This integration to Pubmed that I was mentioning, and then the batch search. By the way, if anyone wants these slides later, please let me know and I can forward them to you. Alternatively, we do post everything to our Figshare account, and you can download every presentation from the past couple of years. The amount of data on here, so 875,000 chemicals. Curation has been going on for over 20 years, even though the application itself has only been online for about 4 years now. Over 700,000 toxicity data points from about 30 sources. And this includes data from tens of thousands of literature articles. We have millions of synonyms and identifiers to make searching as expansive as possible. Tens of thousands of experimental data points for log P, water solubility, flash point. For example, we have 14,500 log P values. Millions of QSAR prediction reports, so multiple endpoints for 875,000 substances has resulted in millions of these prediction reports being generated. We can also do prediction on the fly for chemicals we don't have, and millions of bioactivity data points. So this centralized hub of data is pulling all of that into one seamless application, and it includes then this integration to Pubmed for 29 million abstracts and growing daily. So I'm going to switch to the browser right now, and let me bring up the browser here. It'll take you to the home page. So everything I'm about to show you is accessible to all of you. We have no blockage at all on your access to data, etc. This is no login, no registration required. So starting at the home page, at the moment, you're searching for chemicals is based on CAS number, name, and I'm assuming people will know what an INCHI key is, but I will touch on it briefly if you don't know what an INCHI key is. We do not yet have structure searching in terms of drawing a chemical, but that is in prototype already. We are testing that internally. I'm going to search for a chemical, and I start typing. So it's a type ahead search, and you can see here as I type in atrazine, it is pulling up every single chemical where atrazine is in that particular name. Alternatively, I could start typing a CAS number, and it will find the CAS number this way. We can also do substring searches, so we can come back and do that later. But if you're looking for every chemical that is a bisphenol, you can do a substring search of that nature. So typed ahead to find atrazine, and it is now going to load the chemical detail around atrazine. We land at a very simple page, which we hope is easy to navigate. This is the chemical structure here for atrazine. This is the active CAS number right here, and this is the substance identifier for this particular chemical in question. We call this the DTXSID, which stands for DSS Tox, which is the underpinning database substance identifier. It is a unique identifier, so if we search it on the internet, I'm just copying that now. If I paste it and search Google, it finds it in multiple places. So it finds it in our results set. It finds it on Wikipedia already because it's already been registered directly into Wikipedia. They're starting to show up in articles, starting to show up in other databases. So those are our unique identifiers that are already proliferating across the internet. We've integrated Wikipedia. We feel that this is a useful contribution in terms of giving you a general overview of the chemical. There are over 21,000 chemicals now on Wikipedia, growing regularly, and we try to keep those integrations in place. Quality control notes. In this case, this chemical has no specific quality control notes, but I will give you some examples as we go of why that becomes particularly useful. Intrinsic properties, so not predicted now, just intrinsic. Atomic masses added together to give you the average mass, monoisotopic mass, as well as the formula. This becomes very useful for our colleagues in mass spectrometry who are trying to identify chemicals in the environment, who are using LCMS as an example to do non-target analysis. We give you some simple paths from this point for accessing the data. So if you want to download the mol file to open up in a structure editor at your desktop, download the mol file, one click, and you can do that. If you want to find all chemicals related to atrazine in terms of formula, it will automatically do a search to find by the exact molecular formula what else we have in the database. And some chemicals you will have hundreds of hits for. So that's the intrinsic properties. Structural identifiers, these will be your systematic names, UPAC name, for example, that is generated algorithmically using rules-based software. The SMILES, many of you, I'm aware, will know of what SMILES is. SMILES has an issue, and SMILES are generated by different toolkits. There can be different canonicalization routines. So for one chemical, you can end up with dozens and dozens of SMILES strings. So SMILES is exactly the wrong way to search the internet for a chemical. Rather, there has been an effort over the past almost 2 decades to build something called INCHI. INCHI stands for International Chemical Identifier. If you want the details, anywhere where you see blue in the interface in general is going to be hyperlinked. So if you want to understand what INCHI is, click and it will take you to the Wikipedia page for a description. That's a whole different discussion of how INCHI came about. But when you have INCHIs, and we generate them automatically for every single chemical we register, as does almost every other chemistry database on the internet, when we're all using the same code base, we're all using the same structural representations to generate these INCHIs, then you can link together the internet based on structure. So I want to structure search the internet. There's a couple of ways for me to do it. I can paste this INCHI key directly into Google and do the search. So that's one way, and we found atrazine based on Pubmed, we found it on Chembl, we found it on ChemSpider, we found it on NIST. So you can do it that way, or we just built it directly in. So you're structure searching the web to find the presence of atrazine in many, many other databases across the web. And that is how the internet is now connected together at a structural level. So INCHIs become very, very useful. Linked substances, this is allowing us to connect together our own database to all of its related chemicals. So for example, atrazine may be one component in multiple substances. It may be one component as a salt, or a multi-component system. Easiest thing is to show you. So here we see atrazine is present as the query chemical. It is also right here as a part of NOx-B. Here it's the hydrochloride salt. Here it's a part of marksman. And you can see 25 different chemicals visible. 5 of them are switched off as isotopically labeled. But that was one search to show you every chemical that we have, every substance where atrazine is a component. This is specifically useful for our mass spec group, again, detecting chemicals in the environment. This helps them understand all of the various sources of how that chemical might have found its way into the environment as a component of what particular product. So those are mass spec ready substances. Similar compounds, this is simply a search that we perform in the background to show you similar chemicals. Here we are. There's also another way to get to that, and that's this similar compounds tab on the left-hand side. So what we're starting to do now is we're starting to navigate these tabs on the left. So similar compounds took you to this tab. That's what was going on. We also have presence in lists. So in order to build up a database of 875,000 substances, we have sourced data from many, many lists. Many of these can be inside our own agency, built for our own research purposes. They can also come from external lists where collaborations, maybe specific websites that we've formed relationships with to integrate their data. So now, as we browse through these lists, we see different ones of interest. So pesticides. So we want to look at all of the pesticides on the EPA Office of Pesticide Programs Information Network. Click. So we've now navigated from atrazine into the list of all chemicals that are part of this Office of Pesticide Programs. It's loaded 3,961 chemicals into the interface, and here they are. So you're starting to see what that list is compiled of. You can do that for any of these lists. So if you're interested to see what is in the Thermo's MZ Cloud database, so this is a mass spec database. This has got 4,700 chemicals right here. All of these lists are now navigatable, and we've segregated them into federal lists, US state, international, and others. So various lists that we continue to build together. Let's migrate back to now data quality for a moment. How are we pulling our data together, and how do we ensure quality, and how do we flag that for you as users? So we pull data from various sources. I will show you that we have over 200 individual lists that are public, 875,000 chemicals, 20 years of work sourced from various areas. And what we have to do is we have to quality curate this. We'd like to get everything to the highest level possible. We have 4 full-time curators, and then a number of the PIs we curate and carefully monitor our own data sets of interest. And you can see that under this record information where we show you the different levels of data quality. So level 1, we have about just approaching 15,000 chemicals out of the 875K that we've elevated to level 1. That means we're checking many of the names, the chemical structure, the CAS number. We're looking for consistency between them at the highest level. We put an incredible amount of work to make sure that before we elevate this to level 1. Level 2, we are curating, we are doing a slightly lower out level of curation, looking across multiple sources that we trust, all the way down to level 5, where we are doing comparison with computers, comparing data, looking for consistency. So we have 5 levels of public data and 2 additional internally. Not every chemical we have registered has yet made it to the public. In our next release, it looks like we will be releasing another 8,000 chemicals in March of 2020. This is the URL and citation for this particular chemical, and the URL includes, if you notice right at the end, this DTXS ID. So if anybody sends you the unique identifier, you can always land at the page simply by appending it to the URL. All right, let's dive a little deeper. So the executive summary now gives us a summary view of all of the data that I'm going to browse through for atrazine. So it is telling you in one page here, it is telling you that we have an IRIS value available. So this is the integrated risk information system from EPA. It is saying that it's there. These are external links or inside the application. When you click on this, it has navigated us down the tab right here on the left-hand side, navigated us into the application and highlighted IRIS. It has loaded the web page in real time. These values can change over time, and rather than us try and chase and synchronize the data for all of the different resources we have to integrate, we simply load the page in real time, and that's what this is. It's a load of the IRIS web page. Go back to the summary. We have no PPRTV values available. This is provisional peer-reviewed toxicity values. We don't have any. Regional screening levels available, so we can navigate here, and it will take us into the hazard subtab. But here are some regional screening values right on the page. Anywhere you see an informational icon like this means you can hover, and you can get a description of where the data came from, as well as associated publications and hyperlinks. This is telling you there is a minimum reference dose available, and is telling you it's subchronic data. This will take you directly into the table. We will do that. And on and on and on. As you browse through this page, you can see we have repro tox, chronic tox, subchronic, acute tox. All these data are available. We also have predicted phys-chem parameters. I will show you how we've done that, but it's telling you these are visual cues to tell you that they're in the ranges that you would not worry about too much because of fate, persistence, bioaccumulation, etc. We also have links to the adverse outcome pathway data. So we have linked to the AOP wiki directly. Atrazine has been associated via the bioactivity data we've measured with a particular gene. We will hit into that. That's called ToxCast. and we can also link directly through to the AOP. So this is loading the AOP in real time. Going back to the dashboard, we can also show the bioactivity plots. So at the bottom here, we're showing you all of the bioactivity data that's been measured with active hit calls. Every data point is active. You can browse through. Again, if this is kind of confusing at your first blush, navigate over to the informational icon. It will explain to you what these data are displaying. The same in terms of where the assay data comes from. And then these are the points of departure that we have in the hazard table. And for those of you who've been following our endocrine disruption work, this chemical has been measured in 35 EDSP assays, endocrine assays, looking at the estrogen receptor, and was deemed to be active in only one of those. So these are all of the EDSP assays. This is the ToxCast work. So this is a summary view of the chemical. Now we dive deeper. Properties. So for all of the chemicals that we are doing our best to harvest the data, pull it together, both experimental data, and when we don't have experimental data, then we predict. So you can see we have log P, melting point, solubility, vapor pressure, and pKa values in the experimental column. But we've been able to predict the majority of these when we don't have them. So let's go into log P. We have one log P value. Hover over, it tells you where the data came from. So these are the data that are underpinning the EPI-suite database. We are also harvesting additional data from the literature and expanding on the databases. We have multiple prediction algorithms, some of them commercial, some of them open source. And in all cases, you can see if this is the experimental value, all of them are doing a good job at predicting. The challenge with these prediction algorithms, however, is we don't have transparency into how the predictions were done in all cases. So how was it done? How big was the training set? How big was the test set? None of this information is available directly for these other algorithms. But with Opera, which is our own build of these models, we show you for this chemical the predicted value. We tell you it's inside the applicability domain for the prediction model. We give you a value between 0 and 1 that tells you our comfort level in terms of the confidence level right here, and the local applicability domain. Local applicability domain is related to the chemicals closest to the chemical we're modeling inside the prediction set. How do you see that? We show you the nearest neighbors from the training set directly. 5 different chemicals. It turns out that atrazine itself was in the training set. You get to see the experimental values and the predicted values. This is showing you that we have 14,500 log P values that we've built the model on, and this is showing you the distribution of the entire set of chemicals. So you can see that the log P values are very spread out. So this is one prediction report. I said we had millions, and the reason behind that is for every property that we are predicting, we will show you a prediction. So if we choose melting point, you can see that we have 6 different melting point values, and here's the Opera report. Again, unique chemical inside the applicability domain. This is the breadth of the melting points. This is the data set, and here are the nearest neighbors. So every time we predict, we have a report of that. In that case, what you're looking at is total transparency in terms of the model. Now we want to download these data because we may want to use them in a report. So I'm going to go back to take a look at all of them. I want all of these numbers into an Excel spreadsheet for me to use in a report. Every time you see a table, you have the ability to download it. So this is downloading it directly to my desktop as an Excel file. Double click and it will open up an Excel file and will display this for you. And there you have it. Everywhere you see a table in the application, you can download the data. So we have done a similar thing for bioaccumulation factor, bioconcentration factor, fish biotrans half-life. These are using similar models. This is the FISPROP training set. Here's an Opera model report. So both biotransformation bioaccumulation, etc., etc. Now diving into the hazard data. So we have various types of hazard data available from multiple sources. And I said we have 700,000 data points harvested from over 30 different sources. And you can navigate through these data. You can see the source, Department of Defense. We can show more data on the page. You can rank order the data to see there's lowest values, etc., etc. We can even dive into the original source data. So we're trying to homogenize it from multiple sources into one form for you to browse through. But we show you what the original data was so that you can look back into exactly where we loaded it from, as well as the definition of where this data came from, etc., etc. So we're taking on the hard job of assembling data for you to put it into one form. It is a data set that you might want to download into an Excel file. As I said, every table gives you the data. So there you can see all the data with the sources, with the exposure out, etc., etc. So we have various forms. So the point of departure values will be in here. And we have both eco data, and you can see here the species. Many of these species I don't personally know. Proso millets, duckweed, parrot feather, water milfoil. These are all sourced from the Tox Database. And the Tox Database is another EPA resource that is available. It's a totally separate application built by our colleagues in Duluth. And what we're doing is we're integrating it directly into our system. So now you have a path to navigate between the individual applications. I'll navigate through into exposure data. So what we've been doing is also pulling data from various sources to highlight how these chemicals are being used. And I could stick with atrazine, and you can see it's a pesticide. But just for a moment, I prefer to use something which is where we're all exposed to this chemical in a slightly different way. And I'm going to pull up a chemical called methylparaben. Notice all I'm doing is the type ahead search, find the chemical of interest. So methylparaben is something that most of the people on the call today will probably have showered this morning, and you will be exposed to this particular chemical. Just switching off my email here. It'll be easy to just do this. Okay. All right. Methylparaben. I now go into my exposure, and this is where methylparaben will come into contact with us. So face cream, hand body lotion, hair conditioner, mascara, etc. So there are many, many products that have been associated with this particular chemical. And we've been harvesting the data from various sources. This is work that was done originally by the group in NERL, the Exposure Research Labs. We have had a reorg here at OR&D and EPA, so now we're actually working together under the same center. But this is work pulling the chemicals, the CAS numbers, the names, the weight fractions directly out of SDS sheets on the market. And you can see here we have hundreds and hundreds of records containing this particular chemical, showing you how the chemical is used with the actual name of the individual product, telling you what the source is of this. And we've now, the group has pulled out data from more than 1.5 million SDS sheets. Again, if you want to understand how this work was done, how it came together, you can take a look at the publication directly. We have, for methylparaben, 1,481 records were available containing the actual chemical weight fraction for this particular chemical. So incredibly rich information. Navigating back to the home page for a moment, if you're interested in shampoo or hairstyling or mascara, for example, let's go back to product use categories, and we can type in hair, and you can look at different types of hair color. We can type in pesticide, animal repellent, fungicide. go in and take a look at what's in these individual chemical product use categories. This work continues. We're pulling together some very rich sources of data, all of which will be made available through the dashboard. I said we were integrating other agency resources. So there is the Toxics Release Inventory. Again, separate application now. They are tracking the management of toxic chemicals that have been identified, that we need to monitor their releases. These tables are loaded directly on the fly in real time every time we load the page. So this can all be updated on any given day. These data can change. So that's the Toxics Release Inventory. And we have also been developing exposure models, predicting on a specific level what level of exposure, whether it's based on age, whether it's based on body mass index, male, female, what exposure level you would have in the country. So the NHANES data, I'm sure many of you will have heard of NHANES. This is the CDC effort that have been sampling humans for many, many years now. Our colleague John Wambar has generated some inferences, modeled the data, and generated inferences in terms of the exposure levels you would get on a daily basis for many of these chemicals. Lower 95th limits, upper 95th median. But we've also got work going on here for exposure predictions using something called the SEAM approach. Again, this will now take you directly into the publications about how this was done. We've got this done for about 7,900 chemicals now. The algorithms are going to be applied to every substance that we can model across the entire application. So these will be the new Scene 3 models that we're releasing. Bioactivity dives us into our ToxCast Tox21 data. I showed you this already on the summary page, and for any of you that are using the ToxCast data, you may have been accessing it previously through the ToxCast dashboard, EDSP21 dashboard. Those have now been switched off, and all of the data is surfaced directly through the chemicals dashboard right here. You can see that there are 866 assays that the chemical has been measured in. There are 40 assays for which the chemical has had an active hit call issued. You can see the summary names of these. These may be certainly not descriptive enough for your needs. At any point, you can hover over it. It will give you a definition of what this particular assay is examining, how it was measured, what organism, what tissue, etc. But a full description of an individual assay is available directly under this modal. And this tells you, you can read the articles that led to the development and validation of this assay. Full transparency into how all of our data is processed. You have a direct view of every single step that the data is processed through the pipeline, and then any associated reagents. So just examining the bioactivity data alone is a deeper discussion. If anybody wants to have a follow-up conversation, we can do so. So we also split the data sets into endocrine disruption, because that was a big focus of the agency, to look at a specific set of assays related to estrogen receptor, androgen receptor, thyroid, and steroidogenesis. So now we're diving deeper into that data. What I showed you here was summary data. This is a summary of the hit calls. If you want to actually dive in and look at each of the individual bioactivity curves with all of the data, you can dive directly into the application and see each of the individual curves. ToxCast Tox21, we can do exactly the same. This is now the full expanse of all assay endpoints we've studied. So this is now going to load all of the data, and you can see all of the bioactivity curves here. So again, we're trying to offer transparency into all of the work we're doing in our labs and deliver it to a manner that you can interrogate it. Leaving the bioactivity and moving to similar compounds, we landed here previously when we landed on the page and we looked at the executive summary. the details page. I said you can view the similarity here. You can look at, you can filter these out based on whether they've got isotopically labeled chemicals, multi-component chemicals. Now we have a set of chemicals that are similar to atrazine, and each one of these individual chemicals may or may not have bioactivity data, may or may not have hazard data, will almost certainly have predicted properties. And we want to get to the data for those 55 chemicals as fast as possible. Clearly, you could navigate one at a time. So as I select, I now go into one at a time, and I have to look one at a time at those chemicals. Alternatively, I'm going to go back and switch out the isotopically labeled ones. So now I'm going to send that list to the batch search. So the batch search is available at the top of the page right here. I've sent that list of identifiers through, and now we want to download the data, all the data that we were looking at previously. I want to download the CAS number, the UPAC name. I want to get the mass, the monoisotopic mass, all of the predictions. So let's take the opera predictions. Is there a predicted exposure level? Is there toxicity data available? Has it been measured in ToxCast? So I'm just selecting those. And is there IRIS reports? So for 55 chemicals now, I want to download those data. So what it is now doing is it is taking that list of identifiers, hitting multiple databases, harvesting the data from either of those databases, assembling it together, all associated with that set of identifiers, and pushing it into one Excel file, downloading it to the desktop. And all of the data that we're looking for is now assembled into that Excel file. So here's our list of chemicals. So 55 chemicals. Here are the preferred names. These are the CAS numbers. This is the UPAC name. Where there's a Y, it's telling you that there's predicted exposure levels. The Y here is telling you there is toxicity data available. This is telling you that the chemical was analyzed in 457 assays, 7 active hit calls. There are IRIS reports for 2 of the chemicals. These are all hyperlinked, by the way. Everywhere with this blue is a hyperlink. And then these are all of the predictions. So we landed on atrazine. We found 55 related chemicals, and we were able to pull all of the data into one file just by pushing it into the batch search. So batch searches are great, but you may have a starting point where you want to harvest a specific set of chemicals. So I'm going to go into lists for a moment, and I'm going to say what type of chemicals might we be interested in. So let's assume pesticides. I told you we had a number of lists in here, and there was a couple of hundred. Let's see here, 213 individual lists at the moment. Typing on pesticides, we have six individual lists of pesticides. We update these on a regular basis, so you can see that 3 of these were updated in 2019, actually in October. We're going to take a look at the list of active ingredients in the EPA pesticides list. So now there are 510 of those listed. These are the individual chemicals. We can look at them in different ways. We can view them in a tabular form so that you can see the types of data that we have available. The name, the CAS number. ToxCast is telling you the data has been run through our bioactivity. Number of sources, so those are the number of lists associated with acetaminophen. It's also registered on Pubmed, and we will link into that. And there's also 15,759 articles about acetaminophen on Pubmed. I was wondering myself why acetaminophen was included as a pesticide in the pesticides list, and it turns out it is fed to mice, and then the mice are dropped out of the plains into the jungles to wipe out snakes. I had no idea about that particular project, but it turns out that was the reason for it. I'm going to go into a particular chemical here. Let's choose one of interest. I'm going to say anthraquinone. So I'm now diving in there. And now we're going to go into the literature searching. So the literature searching allows us to connect up with Pubmed or Google Scholar queries. So if all I want to do is search Google Scholar, what we're doing is we're pushing the CAS number and the name, which we have here. The CAS number and the name, and we're going to choose a query term. We want to look at hazard. And all it's done is it's pushed out that simple query. So Google Scholar is very all-encompassing, but it is not highly curated, of course. It's just an index. Pubmed is different. So Pubmed, we are using specific queries that have been generated by one of our colleagues, Nancy Baker, to pull the data together in a manner that she can query out against Pubmed's application programming interface and web services. So this is the CAS number, the name, and what we call the mesh name, also registered into our data set. I'm going to click on hazard, and notice what it's done is it's added this query to the end of the search. So now it hits in real time, and it found 4 articles. I've never looked at this chemical before. When I do live demos, I always choose a different path. So we can look into here to see what type of information is available. So have they done any rats analysis? Oh, turns out the rats are in all of them, and we can take a look why. So as we perform a query, we can see these terms highlighted. Liver. Okay, so now we're looking at this, and you can see increases in liver and spleen weights. This can be done for any chemical of interest. So if we go back here to permethrin, we will now search for permethrin against Pubmed and find what information is available. Literature, Pubmed, permethrin, and maybe we're interested in androgen disruption. Notice it's changing the query here based on our query term. 12 articles. And now again, you can start to query through the article and highlight the terms of interest. This is called Abstract Sifter. There is a version of Abstract Sifter that is built for Excel directly. You can download it here. This is a module that is embedded inside the application. Similarly, we embed resources from other groups. So for example, if you wanted to look at the PubChem articles, you can look here. You can look at the PubChem patents. You can look here. These are embedded systems. While we embed individual modules, we also have this link farm. So this is an opportunity for you now to link out to the world of the web and find other information. So you might be interested in whether or not permethrin is on PubChem. So click, and it will find you permethrin on PubChem. Maybe you want to see the safety data sheet on PubChem. There's a GHS classification. Maybe you want to see whether or not there's a mass spectrum. There's the mass spectrum on NIST. So this is a link farm of over 70 individual sites where we've done the work to connect together the CAS number, the name, the INCHI key, which I introduced earlier, and pull it all together so that you can navigate the web directly from the application. I showed you batch search, and we landed a batch search previously using a list of identifiers because we navigated within the application. What we're going to do instead is bring in a list of CAS numbers, which somebody may have provided to you some other way. We're going to do the search. And it is very common for people to get incorrect CAS numbers. I'm making a small edits here. These transcription errors are common. It's very often that this can happen. And when we navigate the data, we are going to check every one of those for you and see whether or not the CAS numbers pass the valid checks. So from this batch page, we could have downloaded any of the information I showed previously. But when we do that now, we do check all the identifiers. And you can see here the issues. They're not CAS numbers. That becomes very valuable for us when we are registering data. We need to check, we need to validate, and we need to curate. So you can also search by CAS numbers, by names, etc., etc. So the batch search is very enabling that way. Just a couple of minutes left, really, to show you that while I was focused on navigating chemicals, we can also do searches based on mass and formulae to serve mass spectrometry. So here's an example of looking for a mass of 300.1 plus or minus 5 ppm. The reason that we display the data in this particular way is with this tabular form, is to help people rank it using information. So we've already proven with a couple of publications that when you have metadata such as number of products that a chemical is contained in, whether or not it's been published on a lot, so we call this just candidate data for ranking the hits. So this allows you to rank the data. So you can source and rank the data in this way. Every time you see a list of chemicals, of course, download it into an Excel file. The lists of chemicals that I showed you only pesticides, but we do work on multiple projects that are of interest. So as an example, a recent query around terpenes in vape, we assembled that list. Maybe you're interested in opioids. So we build these lists specifically, and we do try to link them back to websites of interest. If you feel there are lists that we should integrate here, please make us aware of them, and we'll do the work of linking them in and curating them. When we don't have all the chemicals of interest to you, it is possible for you to take advantage of our real-time predictions. So in this case, I'm going to bring in atrazine, which we know we have because I showed you how to search on atrazine and look at all the data. But now we're going to have a new chemical that's not been seen before in our database. And now all of these predictions that we have here, these are the toxicity estimation software tool predictions. We're going to perform those calculations in real time. And then there were actually 4 models that were performed in real time then. It's built a consensus model, and then you can actually see the report for how that model was built and the performance of that model for this individual chemical. So that's real-time prediction. We don't yet have this available as a batch, but we are building a batch version so you can submit thousands of chemicals and perform these predictions in batch. All of our chemicals are downloadable in various formats, so you may want all of our CAS numbers, names mapped to substance identifiers. You might want our entire data set of 875,000 substances. You may choose to download our synonyms, millions of synonyms, and all the curation work that we've done. So if you're building your own internal systems, we try to put a lot of our downloadable data here for you to utilize. I'll return home, and I will take any questions with the 7 minutes that we have left.